helm, steady as she goes. All hands, battle stations.
Target is bearing 040, range 15,000 yards.
15,000. Adjusting for wind and elevation, sir.
Confirmed.
We're getting a solid return here.
Yes, the frequency is locked. Maintain observation.
December 3rd, 1941, North Atlantic. Before dawn, a U.S. Navy destroyer cuts through black water at 14 knots. The sea is calm, but the air is tense. On the bridge, officers peer into darkness that feels endless. Beyond the bow, there is nothing. No lights, no horizon, no warning. Only cold wind and the faint glow of instrument dials. Lookouts strain their eyes. Binoculars sweep empty space. Sound-powered phones crackle with routine reports. The ship is blind beyond a few thousand yards, relying on human sight and instinct, the same way fleets have done for centuries. Somewhere ahead, unseen, steel may be moving. A submarine periscope could already be raised. A surface raider could be crossing silently. In 1941, at night or in fog, the ocean still belongs to whoever is hidden best. Below decks, there is no humming screen, no sweeping line of light, no early warning. The U.S. Navy, the world's largest fleet by tonnage, sails without a true naval radar shield. Within days, the illusion of distance and safety will collapse. And in that collapse, an improving technology, rushed from laboratory benches into warships, will decide who sees first and who never sees at all. In 1941, the United States Navy still thought in daylight. Its doctrine had been shaped by gunnery ranges, visual signaling, and the long traditions of surface combat. Battleships were built to see the enemy and be seen. Destroyers hunted by sound and silhouette. Night fighting existed, but it was considered a specialized skill, not a foundation of naval power. Across the Atlantic, the war was already proving that assumption obsolete. Since September 1939, Britain had been fighting a war of darkness. German U-boats attacked at night. Surface raiders slipped through fog and weather. Air raids came without warning. In response, British scientists had turned electromagnetic theory into a weapon. Radar, still crude, still temperamental, was already reshaping how Britain survived. The chain-home radar network guarded the British coast. At sea, early naval radar sets were being installed on cruisers and destroyers, allowing ships to detect aircraft and surface contacts beyond visual range. These systems were not elegant. Displays flickered. Accuracy was limited, but they worked often enough to matter. The United States knew this, but knowing did not mean acting. Before the war, American radar development was scattered. The Naval Research Laboratory in Washington, D.C., had been experimenting with radio detection since the early 1930s. By 1937, researchers had successfully detected aircraft using reflected radio waves. Prototypes existed. Demonstrations impressed visiting officers. Reports were written, yet progress moved slowly. Part of the hesitation was institutional. The Navy already possessed sound detection, sonar for submarines. Surface threats were assumed to be visible. Aircraft were believed to announce themselves. Radar, to many senior officers, felt redundant, fragile, and untested in fleet conditions. Another obstacle was industrial. Radar required precision electronics, vacuum tubes, stable oscillators, sensitive receivers. The American electronics industry in the late 1930s was oriented toward consumer radios, not rugged military systems. Production tolerances were inconsistent. Environmental durability was uncertain. Most importantly, there was no urgency. The United States was still officially at peace. By 1940, Europe was burning, but American warships sailed neutrality patrols, not combat operations. They shadowed convoys. They reported contacts. They avoided engagement. The Navy had time, or so it believed. That illusion began to erode as the Atlantic grew more dangerous. German U-boats expanded their hunting grounds westward. Sinkings increased. Neutral shipping vanished without warning. Night attacks proved devastating because they exploited blindness. At night, a submarine commander could surface, use superior optics, and strike before being detected. The British understood this weakness intimately. Radar was not just detection, it was survival. American observers embedded with the Royal Navy returned with troubling reports. Ships equipped with radar survived more often. Convoys with radar escorts were harder to surprise. The technology was imperfect, but it shifted initiative. Inside the U.S. Navy, opinions began to change, but slowly, unevenly. The Naval Research Laboratory continued refining experimental sets. Early models, such as the CXAM radar, showed promise. They could detect aircraft at tens of miles. Surface detection was possible, though unreliable. The systems were bulky, maintenance-heavy, and required trained operators. Training itself became another barrier. Radar was not intuitive. Operators had to interpret abstract signals, blips, and echoes, rather than physical objects. Mistakes were common. False contacts frequent. In peacetime, these flaws were tolerable. In war, they were dangerous. By early 1941, the Navy faced a contradiction. Radar clearly worked, but it was not ready. And yet, war was approaching faster than readiness. The question was no longer whether radar would be needed, but whether American industry could produce it fast enough, strong enough, and in numbers large enough to matter. That question would soon force the Navy to look beyond its traditional suppliers and toward a company not yet associated with naval warfare, but capable of transforming fragile experiments into hardened machines. By mid-1941, the Atlantic was no longer distant. American destroyers escorted convoys as far as Iceland. Neutrality patrols blurred into undeclared combat. Reports from the sea arrived daily, shadowing U-boats, sonar contacts lost in heavy seas, ships disappearing without distress calls. The ocean had become a place where warning rarely preceded destruction. At night, the imbalance was unmistakable. German submarines exploited darkness with discipline. Commanders surfaced after sunset, using the curvature of the earth and blackened seas to approach convoys unseen. Lookouts failed. Guns remained silent. By the time flares or tracer fire erupted, torpedoes were already running. Radar could have changed this, but most American ships still did not have it. The Navy possessed a handful of experimental sets, CXAM and CXAM-1, but these were exceptions. Installation was slow. Production was limited. Each unit was effectively custom-built, assembled with laboratory care rather than industrial speed. The bottleneck was not invention. It was manufacturing. Radar required components that pushed the limits of American electronics production. High-frequency vacuum tubes failed under vibration. Receivers drifted out of calibration. Antennas corroded under salt spray. Early displays were dim, unstable, and difficult to read in rough seas. RCA and General Electric were involved in electronics research, but their facilities were already strained by other defense priorities. The Navy needed a company that could take unstable designs and turn them into repeatable, rugged systems, fast. That search led to Westinghouse Electric. Westinghouse was not a naval specialist. Its strength lay in heavy industry and precision manufacturing, turbines, generators, transformers. The company understood how to build equipment that survived vibration, heat, and continuous operation. More importantly, it understood scale. In late 1940 and early 1941, the Navy quietly expanded contracts. Westinghouse engineers were brought into radar development programs not to redesign theory, but to make it manufacturable, to make it survive. This was not a clean transition. Designs arriving from laboratories were incomplete. Specifications changed weekly. Performance targets shifted as new intelligence arrived from Britain. Engineers worked without finalized doctrines, often modifying equipment already on production lines. At the same time, training lagged behind installation. Ships received radar sets without experienced operators. Manuals were rewritten mid-deployment. Crews learned by trial, error, and improvisation, sometimes during live patrols. Yet pressure mounted relentlessly. In June 1941, Germany invaded the Soviet Union. The Atlantic campaign intensified. U-boat numbers increased. American losses rose, even without a formal declaration of war. Inside the Navy Department, radar shifted from experimental asset to strategic necessity. Westinghouse accelerated. Factories retooled. New production lines were assembled for radar transmitters, receivers, and power supplies. Quality control standards tightened under naval oversight. Equipment was redesigned for shock resistance, moisture sealing, and ease of maintenance at sea. By late 1941, the first wave of Westinghouse-produced naval radar systems began reaching operational units. They were still crude by modern standards. Resolution was limited. Reliability was uneven. But for the first time, American ships could see beyond darkness and weather. The transformation was not yet complete. Many captains remained skeptical. Some trusted their eyes more than screens. Others feared over-reliance on unfamiliar technology. Then, in December, everything changed. War arrived not gradually, but violently. And radar, unfinished, imperfect, and urgently needed, will be tested not in exercises, but in survival. From that moment forward, radar was no longer an experiment. It was a wager placed on electrons, industry, and human adaptation. The arrival of radar did not change the Navy all at once. It fractured experience. Some sailors adapted quickly. Others resisted. And between them stood a machine that spoke a new language, one learned only under pressure. Radar operators were often junior enlisted men, pulled from radio or electrical ratings and given weeks, sometimes days, of instruction. They learned to read glowing lines and unstable blips on cathode ray tubes. There were no silhouettes, no scale models, only abstract movement translated into meaning. Fatigue made interpretation harder. Sea conditions distorted returns. Rain and waves created false echoes. A careless adjustment could erase a contact entirely. Operators learned caution the hard way, knowing that a missed signal might cost lives. Above them, bridge officers faced a different challenge: trust. Radar reports contradicted instinct. Contacts appeared where nothing could be seen. Ranges exceeded human vision. Bearings shifted silently. Accepting radar meant surrendering centuries of naval intuition. Some captains embraced it immediately. Others hesitated, ordering visual confirmation before acting. In combat conditions, that hesitation could be fatal. Early naval radar sets were fragile. Vacuum tubes burned out without warning. Transmitters overheated. Power supplies fluctuated with ship generators. Salt air corroded connectors faster than designers expected. Westinghouse engineers worked constantly to stabilize these systems. They reinforced housings, improved tube sockets, modified cooling paths. Every improvement came from failure, reported from ships at sea. Radar was not yet a weapon. It was a tool under construction. The Navy had built its command culture on hierarchy and certainty. Radar introduced ambiguity. A screen showed probability, not fact. Decisions had to be made with incomplete information. Training doctrines lagged behind reality. Manuals assumed ideal conditions. Combat rarely provided them. Officers had to decide whether to maneuver based on signals they barely understood. Yet slowly, patterns emerged. Ships that used radar aggressively survived more often. Convoys with radar escorts detected threats earlier. Night no longer belonged exclusively to the enemy. These lessons spread informally, through after-action reports, word of mouth, and quiet observation. Radar was not winning the war yet, but it was changing how sailors experienced it. And as human trust grew, the stakes rose. Because the enemy, too, was adapting and watching. While American crews learned to interpret glowing screens, their adversaries were learning how to exploit the absence of them. German U-boat commanders in 1941 understood their advantage. Many Allied escorts could hear submarines underwater, but only after an attack had begun. At night, surfaced U-boats were faster than most convoys and often invisible until they fired. Radar threatened this balance. Intelligence reports soon reached German command that some American ships were detecting contacts in poor visibility. Suspicion grew. U-boat captains were instructed to be cautious near escorts suspected of carrying radar. Periscopes were raised briefly. Attacks adjusted. The unseen war had begun to shift. Inside Westinghouse plants, production ran around the clock. Skilled workers were scarce. Components arrived late. Blueprints changed without notice. Engineers worked directly alongside machinists, revising designs as parts were assembled. This was not peacetime manufacturing. There was no margin for perfection, only urgency. Each radar set represented compromise. Performance balanced against reliability. Speed balanced against durability. Every shipped unit carried known flaws, but also life-saving potential. The Navy sent ships to sea with equipment still evolving. Crews trusted systems that might fail without warning. Engineers knew their designs were incomplete, but delay meant blindness. There were no ideal choices, only acceptable risks. By late 1941, radar was neither experimental nor mature. It existed in a dangerous middle ground, where success depended as much on human judgment as machine capability. Then the strategic situation collapsed into clarity. On December 7th, 1941, the United States entered the war. From that moment, radar was no longer optional. It was a requirement, regardless of flaws. Production accelerated further. Installation became standard. Training intensified. What had been a cautious transition turned into a full-scale transformation. The technology had crossed a threshold, and now it would face its decisive test. Not in laboratories or factories, but in open ocean combat, where detection meant survival and delay meant loss. January 1942. The Atlantic at night. American destroyers and escort vessels move in loose formation around slow merchant ships. The sea is darker than before, not because the moon has changed, but because certainty has vanished. The United States is now at war, and the enemy is no longer hypothetical. Below decks, radar rooms glow faintly. Operators sit forward, headphones pressed tight, eyes fixed on unstable green traces. The sweeping line returns again and again, each pass rewriting the picture of the sea. At first, it is noise, static, sea clutter. Then, something else. A faint return, steady, moving against the convoy's course. A report goes up to the bridge. There is nothing to see. This moment defines the turning point. Not contact, but decision. Some captains order investigation immediately. Courses change. Speed increases. Searchlights remain dark. Guns stay silent. The ship moves based on what cannot be seen. Other captains hesitate. Radar is still new. False echoes are common. Turning a convoy based on a single blip feels reckless. Minutes pass. The contact fades or erupts. The first confirmed successes come quietly. A destroyer escorts a convoy off the eastern seaboard. Radar detects a surface contact at night, well beyond visual range. The ship closes. Star shells illuminate the sea. A surfaced U-boat dives hard. Depth charges follow. Oil appears. Debris surfaces. The convoy continues. There is no dramatic announcement. No headline. Only an after-action report noting that radar contact preceded engagement. Similar encounters repeat through early 1942. Not every detection leads to destruction. Many end in evasion. But the pattern is unmistakable. Radar gives time. Time to maneuver. Time to alert. Time to deny surprise. Westinghouse-produced systems are now at the center of this shift. Their reliability is inconsistent, but their presence changes behavior. Escorts begin to trust early warning. Convoys tighten formation at night. Lookouts stop being the sole guardians of safety. But radar does not solve everything. Operators struggle with interpretation. Sea clutter mimics targets. Rainstorms distort returns. Enemy submarines adapt, limiting surface exposure. Some attacks still succeed. Losses remain heavy. What changes is initiative. For the first time in the Atlantic War, American escorts can act before torpedoes run. Each detection reinforces confidence. Each failure prompts adjustment. Engineers assure revised designs based on reports from the sea. Crews refine procedures under fire. Radar, once experimental, is now embedded in survival. Yet this is only the beginning. Because while early successes prove possibility, the full transformation, industrial, doctrinal, and psychological, has not yet taken hold. And it will take a catastrophe far larger than any convoy battle to remove all remaining doubt. December 7th, 1941 had shattered illusion. But 1942 would destroy hesitation. As Japanese forces advanced across the Pacific, the U.S. Navy was forced to confront the consequences of technological unpreparedness on a global scale. Ships burned in daylight. Aircraft struck without warning. Detection failures were no longer theoretical. They were catastrophic. In the Atlantic, the crisis deepened. German U-boats surged along the American coast in what became known as the Second Happy Time. Merchant ships were sunk within sight of shore. Cities blacked out late. Convoys were scarce. Escorts were overwhelmed. Radar was not a cure, but it was one of the few tools that could shift the balance. In early 1942, the Navy accelerated installation at unprecedented speed. Westinghouse production lines expanded again. Simplified radar variants were approved for faster deployment. Standardization replaced experimentation. Training pipelines widened. Radar operators were no longer specialists. They were necessities. Doctrine changed under pressure. Night fighting manuals were rewritten. Radar plots became central to command decisions. Officers learned to maneuver by instrument, not instinct. At sea, the impact became measurable. Radar-equipped escorts detected surface-running U-boats earlier. Surprise attacks became riskier. Submarines were forced to dive sooner, losing speed and attack position. Convoys gained precious minutes, often the difference between evasion and destruction. Failures still occurred. Equipment malfunctioned. Contacts were missed. But absence of radar was now recognized as a fatal disadvantage. By mid-1942, radar had crossed its decisive threshold. Not because it was perfect, but because it was everywhere it needed to be. Westinghouse systems formed a significant portion of this network. Their designs were refined through relentless feedback. Vibration resistance improved. Displays stabilized. Reliability increased with each production run. The Navy's relationship with technology changed permanently. Radar was no longer an add-on. It was infrastructure. This transformation marked the true turning point. Not a single battle, but a shift in how war was fought at sea. Detection became continuous. Surprise became harder. Darkness lost its dominance. The ocean was still dangerous. Losses continued, but the future had tilted. And with that tilt came consequences, strategic, industrial, and human, that would define the remainder of the war. By mid-1942, the Atlantic War had changed irrevocably. Convoys escorted by radar-equipped destroyers and corvettes no longer moved blind. Contact reports reached bridge officers minutes earlier than before. Ships could maneuver, anticipate attacks, and sometimes strike first. Even imperfect radar provided a critical edge. The ocean was no longer entirely the enemy's domain. Statistics began to reflect this. Convoy loss rates, which had peaked in early 1942, gradually declined where radar-equipped escorts were present. The correlation was undeniable. Survival increasingly depended on electronics as much as seamanship. For crews, the psychological shift was profound. Where once darkness was a source of anxiety, radar brought cautious confidence. Operators knew that the glowing sweep of the cathode ray tube was more than a line. It was a lifeline. Bridges learned to act on signals rather than waiting for visual confirmation. Mistakes still happened, but the margin for error widened. Training became formalized. Radar operators followed standard protocols. Daily drills reinforced interpretation skills. Officers incorporated readings into tactical planning. Ship logs began including radar contacts as routine entries, a sign that the technology had become operational reality rather than experimental curiosity. Westinghouse's role cemented industrial-military collaboration. Factories that once produced turbines, generators, and household electronics were now essential to war survival. Engineering teams remained embedded in production lines, iterating designs based on frontline reports. These feedback loops allowed rapid improvements. Vibration-resistant mounts, water-sealed housings, and stabilized cathode ray displays became standard. Yet, even as victories accumulated, the limitations were clear. Early radar could detect, but not destroy. Operators could warn, but engagement still relied on guns, depth charges, or maneuver. Night attacks still occurred, and losses reminded crews that radar was an advantage, not invincibility. Across the Atlantic, German commanders noted the change. U-boats were forced to modify tactics. Surface attacks at night became riskier. The element of surprise, the cornerstone of submarine strategy, was eroding. Enemy adaptation reinforced the value of radar. Every operational success strengthened the argument for accelerated production and deployment. Radar had transformed from experimental gadget to strategic enabler. But the war was far from over, and the full impact of this technology was still unfolding. By late 1942, radar had shifted the very calculus of naval warfare. Convoys became less vulnerable. Escort commanders relied increasingly on screens to plot positions, predict submarine courses, and coordinate group maneuvers. The technology created a new layer of visibility that stretched beyond human sight, changing both tactics and psychology at sea. Westinghouse's production output had multiplied. From a handful of experimental units in 1941, hundreds of sets were now in service across destroyers, cruisers, and escort carriers. Factories ran continuously, producing transmitters, receivers, antennas, and power supplies. At scale, The company had effectively become a strategic arms manufacturer overnight, bridging the gap between laboratory innovation and operational necessity. The Navy adapted its doctrine to match. Pre-war emphasis on daylight gunnery shifted toward round-the-clock surveillance. Training manuals codified procedures for radar-assisted navigation, threat detection, and night combat. Radar plots, once considered abstract instruments, became essential for tactical decision-making. Officers learned to trust readings over intuition, a profound shift for a culture built on centuries of visual seamanship. Operational consequences were tangible. U-boat sinkings began to rise where radar-equipped escorts operated. Convoys that might have been annihilated in darkness now survived, sometimes even turning the tables on attacking submarines. The invisible war, the one fought in electrons and radio waves, had begun to favor the Americans. Yet the technology was imperfect and lessons were hard-won. Operators still misread echoes. Equipment failed under heavy weather. Crews improvised repairs mid-patrol. Losses, while reduced, continued to remind sailors that radar was a tool, not a shield. Strategically, the radar program marked a permanent transformation. The integration of electronics, industrial capacity, and naval doctrine created a model that would endure beyond the war. It accelerated the U.S. Navy's transition into a modern, technology-driven force capable of projecting power at night, in fog, and across the vast Atlantic. In the broader sense, radar's introduction signaled a new type of warfare, one where survival increasingly depended on the unseen, the calculated, and the manufactured, where electrons could decide life and death as much as guns and torpedoes. Radar changed the rules of the sea. It made darkness negotiable, fog readable, and distance survivable. What had begun as an experimental, fragile technology became an invisible guardian for sailors facing threats they could not see. Westinghouse's rapid industrial response proved that innovation alone was not enough. Survival demanded scale, precision, and adaptation under relentless pressure. The collaboration between engineers, manufacturers, and naval operators created a template for modern warfare, where technological capability and human decision-making intersected continuously. For the men at sea, radar was both reassurance and responsibility. Operators learned to trust abstract blips as signals of life or death. Officers learned to act on probabilities rather than certainties. Mistakes could still be fatal, but hesitation became costlier than risk. In the broader sweep of history, the introduction of radar marked a turning point not just in World War II, but in naval warfare itself. It shifted the balance from purely human senses to electronic awareness, from instinct to calculated response. The U.S. Navy emerged from 1942 not just larger, but fundamentally smarter, capable of operating at night, in storm, and against enemies who had once ruled the darkness. Ultimately, radar demonstrated that wars are won not only by courage and steel, but by the quiet, glowing pulse of unseen technology. A signal on a screen, a flicker in the dark, could decide the fate of ships, crews, and entire campaigns. In that sense, Westinghouse's early systems did more than detect threats. They redefined what it meant to survive at sea. This is how a fledgling technology became an invisible sentinel, shaping victory long before the guns ever fired.